Okay, I want to talk about Mach's principle. And Mach's principle is basically this idea that take a person twirling around. They're twirling around, and while they're twirling, they see that the background universe is spinning relative to them, and that their hands are moving outwards. Now, Mach's principle is this idea that that is not a coincidence, that a person experiences a centrifugal force because relative to the background stars, they are twirling around. Now, imagine a universe which consists of just a ball, and you accelerate this ball, but then we reach a problem. The idea that you can accelerate or move this ball in any way is fallacious because it needs something in reference to move to. If it doesn't have a reference frame by which to move, it can't experience an acceleration. So if you apply it to this universe, it basically means that the universe cannot rotate. It's impossible for the universe to rotate because what does it rotate in reference to? It could be spinning 1,000,000 miles a second. It could be rotating 10 times a second. But without saying with what it's in reference to, it doesn't make any difference. So I thought of this universe. Suppose there's a universe in which rotations are relative. There's no such thing as an absolute rotation. And the universe consists of a ball and a donut. And such that the ball is rotating in one direction and the donut is spinning in the opposite direction. There's a relative rotation between the ball and the donut such that angular momentum is conserved. The angular momentum of the ball spinning in one direction is equivalent to the angular momentum of the donut around it spinning in the opposite direction. What's interesting is, imagine that the donut has a larger but comparable moment of inertia to the ball. There's a relative rotation between the ball and the donut, but you're fixed to the frame of reference of the donut. The donut, the ball would seem to be spinning around, but there would be a discrepancy between your known laws. Like you would see the centrifugal bulge on the ball, but it wouldn't match the observation of the rate at which it's spinning relative to your frame of reference. So basically, it would the centrifugal force would be saying that the ball is not spinning as fast as it is. And if you compare this to galaxies, for instance, there's something called a rotation curve discrepancy. And the rotation curve discrepancy is basically based on our known laws, like Keplerian laws. There's a discrepancy between the rate of rotation of the stars in our galaxy to the observed rate of rotation, the angular velocity of the galaxies that we see through astronomical observation. So the good thing about this ball and donut scenario is that it seems to describe how the universe looks, at least on the surface. But when you investigate it further, you see all sorts of differences. The most obvious one being is that in this scenario, the donut's moment of inertia is comparable to that of the ball, in order for which there is an observed discrepancy. Without it, there is no observed discrepancy. If the moment of inertia, in other words, of the donut, were incredibly large compared to that of the ball, the ball's rotation would approach absolute, and there would be no discrepancy between the centrifugal observation and the observed rate of rotation. It would approach absolute. And that would be the moment of inertia of the universe compared to a galaxy. So it doesn't really explain why there would be a rotation curve discrepancy. And second would be the acceleration of the universe. So imagine now that the donut consists of point-like masses that are not bound to one another in any way. Would they experience a radial acceleration outward from the ball? And the answer is, well, it would at first, but then that would dissipate with time. Like when you're spinning a string with a ball, you're spinning a ball with this string attached to the center, and you let go of the ball. The moment that you let go, there's a radial acceleration equal to velocity squared over r. But that acceleration gets less and less the longer the ball is let go of, until the radial velocity of the ball approaches the initial tangential velocity when you let go of it in the first place. So this doesn't describe like an accelerated expansion of the universe. It would be slowing down. The acceleration would be slowing down, in other words. And because you're looking out in space, in both space and time, you're actually looking back in time when you observe something far away. And so it should show that the rate of expansion, the accelerated rate of expansion, is slowing the further away the universe gets from itself, if that makes any sense. That concludes the video on Mach's principle. I just wanted to add one point. The reason why I'm so fixated on Mach's principle is because it's so strong with a priori principles. Like, just the logic of it is very, very strong. But it's a mystery to me why it doesn't apply to our universe. It's a deep mystery.